Home to a diverse yet fragile range of ecoregions, the interior of Western Canada is experiencing unprecedented change. These landscapes range from the rugged Canadian Rocky Mountains in the west, the water towers of the region's major rivers, to the rolling hills and prairies of Alberta, Saskatchewan and Manitoba in the south, and in the north to the subarctic taiga and Arctic tundra of the Yukon and Northwest Territories. The boreal forest, one of Canada's and the world's most important landscapes, stretches across the region from west to east. Each of these ecoregions plays a distinct role in the hydrological cycle, affecting precipitation and evaporation processes and the storage and movement of water throughout the area's rivers, lakes and groundwater aquifers. These magnificent landscapes are cold environments where snow, ice and frozen soils control the storage and release of water. But with some of the world's highest rates of warming, they're losing their cold. The landscapes and their rivers are changing, with melting glaciers, declining snow and ice cover, thawing frozen ground and changing water cycles. We're seeing impacts on terrestrial and aquatic ecosystems and changing extreme events, flood, drought and wildfire.
My name is John Pomeroy. I am the Canada Research Chair in Water Resources and Climate Change, Director of the Centre for Hydrology, and a member of the Global Institute for Water Security. We're now at the crown of the continent. The water from this ice field flows out to the Athabasca River, down to the Mackenzie in the north. It flows into the Saskatchewan River system, down to Hudson Bay, and the west side of it forms the Columbia River system, which flows into British Columbia and then down into the Pacific Northwest US. So water from this glacier is tremendously important to all of northwestern North America.
I'm Howard Wheater, Canada Excellence Research Chair in Water Security and Director of the Global Institute of Water Security at the University of Saskatchewan. We're here on the shores of the Saskatchewan River, which is one of the most important river basins for the prairie provinces of Western Canada. The Saskatchewan River is home to nearly 4 million Canadians and covers 400,000 square kilometres, Alberta, Saskatchewan and Manitoba. Another important river is the Mackenzie River Basin, further north, which covers nearly 2 million square kilometres and the provinces of British Columbia, Alberta and Saskatchewan, as well as the Northwest Territories and Yukon. The source water for both of these river basins comes from the Rocky Mountains, but climate warming is changing the snowpacks and melting the glaciers that feed and maintain the river flows.
Alpine areas in the Rockies have experienced substantial temperature increases and changes to the nature of precipitation. And the glaciers, which are retreating because the snowfall inputs to the glaciers are exceeded by the summer melt of the glaciers. We see evidence for this in permafrost decreases, where permafrost thaw is responding to shorter snow seasons, longer summers, and warmer temperatures. And we see this in the decline in the snow-covered period and decrease in snow cover at lower elevations. If you were traveling through the Canadian Rockies in the early 1900s, you might have had this view here of the Peyto Glacier. This photograph was taken by the Vaux family, and Henry Vaux, a descendant of the original Vauxes who took that photograph, took this photograph in 2002. Since that time has retreated further, hundreds and hundreds of meters further up. We're seeing ice losses of 5 to 6 meters of ice per year melting down every year as it is in its final decline. Sometimes it's difficult to look at temperature records and other things to get a feel for what climate change means. But when you see photographs like this, of this sort of change, just over a century, they can see that our landscape is utterly changing. And when we look forward for the next century, no vestige of the Peyto Glacier will exist. So once they start to melt and start to flow, it would take an exceptionally cold, wet period to cause a recovery. And so even the last few winters have been really snowy. These things are still retreating. It's not enough.
We are undergoing the most rapid warming of the planet's cold regions in the history of humanity.
In Western and Northern Canada, we've had tremendous warming over the last 75 years. In Northwestern Canada, winter minimum temperatures have gone up by 8 degrees, and average temperatures gone up in the region of 4 to 5 degrees. Further south here, we're seeing average temperatures going up 2 to 3 degrees, and winter minimums going up 4 to 5. So that's a tremendously fast warming. It's faster than other parts of Canada, and faster than many other parts of the world.
Across Western Canada, the minimum winter temperatures have experienced the greatest amount of warming. This has resulted in a later freeze-up and earlier snowmelt. The warming's also resulted in a greater proportion of precipitation falling as rainfall rather than snow, reducing the amount of snow depth and shortening the duration of snow cover by 1 to 2 months since the early 1970s.
In the Mackenzie, there's been more warming and exceptional winter warming of 8 degrees Celsius for minimums in that case. As a result, higher but earlier stream flows occurring in that watershed. And of course, declining permafrost and shrubification, which the spread of shrubs into the tundra holds much more snow in place and accelerates permafrost thaw, can also change stream flow.
We've certainly observed changes in the Mackenzie Basin with respect to permafrost. In the discontinuous permafrost areas around Fort Simpson and in the boreal forest around that region, there's well-documented evidence from investigators at CCRN, particularly from Wilfrid Laurier University, who spent a lot of time looking at the impacts of discontinuous permafrost and its change. So it's been noted that it's changing the hydrology. It's changing the flow pathways, and there's less and less permafrost in those regions, and that's been well documented on a few small basins.
The impacts of climate change, including permafrost thaw and other impacts, is bringing to the north a lot of uncertainty about the future availability and the future quality of water resources. The change you can almost see year to year. The climate's getting warmer, the ground is changing, the ground's subsiding, you're seeing forests turning into wetlands. It's so rapid, you just don't see that in southern Canada. And the implications of that are uncertain.
I've had the opportunity to work in sites up in the tundra, north of Inuvik, all the way down to beautiful peatland sites where permafrost thaw is impacting the way those systems are functioning. The north is warming up faster than any other place on the planet. Community members are having difficulty accessing places that they've used on the land because the land is thawing out. I'm a forest ecologist, and my research program up here in the north is focused on how climate warming is impacting northern boreal forests. And there are direct impacts of climate warming, including those of temperature and changing rain and snowfall, but also indirect effects, including thawing permafrost and changing wildfire conditions that impact what species can grow in different places and how those forests function.
I think it's really important to do this research in Canada's north because as climate change continues to influence the fire cycles, we expect to see more frequent fires. So right now we're seeing fires come through every 50 to 200 years, but we expect that to become more frequent with climate change. We want to see how the forests of the Northwest Territories are responding to severe fires. So in the boreal forest, fire is a natural process. It happens regularly, and many of the species here are adapted to it. But with a changing climate, we're seeing more frequent, more severe, and more intense wildfires. And so we want to know if the tree species and understory vegetation in the Northwest Territories is able to recover after these extreme fires.
Impacts on river flows throughout Western Canada are varying, both seasonally and regionally, due to the topography and complex and varied nature of the environmental and climatic changes. River basins in the Canadian Rockies are fed by melting summer snowfields and glaciers, and they've seen a decline in late summer stream flows, whereas in the prairies, some rivers have experienced increasing summer floods.
The South Saskatchewan River obtains roughly 80% of its water from the Rocky Mountains. And of that water, 60% approximately is snowmelt, and a smaller proportion, generally less than 3%, is ice melt from glaciers. But the snowmelt is critically important because it peaks in June at the same time as irrigation demand peaks in the prairies. And so this is right now tied in very nicely to human water use in the area. And in a similar way, the glacier melt, even though it's a small proportion overall, is important in late summer and in drought periods when other sources of water are depleted. And so then helps to reduce the variability of flows, particularly drought water flows in the Saskatchewan River system.
Most prominently in northern areas, an increase in the fall and winter discharge of many streams has been observed due to melting permafrost and its impacts in changing the connectivity of bogs and wetlands to streams. Other changes, such as the earlier timing of spring snowmelt and ice cover breakup, are clearly observed across much of the region.
There's a very vivid statistical trend of increasing earlier breakup events. So breakup has advanced by about a week in the last century, and that increase has been more significant in the last 3 decades as well. Prior to 1989, there were 2 April breakups going back to 1896, and after that year, there have been 8. Historically, there's been quite a range of breakup from April 28th to May 28th. But a couple of years ago, 2016, we had a new record. Breakup happened on April 23rd, shattering the previous record by 5 days. So it's just phenomenal. We noticed a significant warming in air temperature, and as a result of that, it's changed the river ice dynamics. The most noticeable characteristic is breakup timing and freeze-up timing.
Western Canada has experienced some of its most devastating and extreme natural disasters since the turn of the 21st century. Although such disasters have impacted the region since long before settlement, these events are becoming more frequent and widespread, setting records in terms of damage, cost, severity, and spatial extent. Millions of people have been impacted in recent years, with lives lost and billions of dollars in damage to property and infrastructure. Western Canada has experienced extreme and record-breaking fire years for 4 years in a row. Northwest Territories, 2014, Saskatchewan, 2015, Alberta, 2016, British Columbia, 2017. Drought at the turn of the millennium was Canada's most expensive disaster at that time, with drastic impacts on agriculture and the economy. Then major flooding impacted the Assiniboine River Basin in 2014 and the Saskatchewan River in 2013, with the city of Calgary underwater and severe damage and loss of life in other communities. And recent droughts have followed closely on the heels of wet years, with the most severe single-year drought in Alberta in 2015. These extremes have occurred against a backdrop of a rapidly changing environment due to climate change and human impacts of land and water management. Monitoring and diagnosing these unprecedented changes and trying to understand what the future holds for the changing environment in Western Canada's interior is key to the future security of Canada and also the world. This has exacerbated pressures on our land, water and vegetation, posing important challenges for society. How do we manage water security in the face of rapid change and uncertain water futures? Running a major project called the Changing Cold Regions Network. It is probably the most exciting program anywhere in the world at the moment. The Changing Cold Regions Network is all about environmental change. The heart of our program has been looking at the changes in the historical record, understanding the way in which the landscape is evolving, and then building models so we can project into the future. Changing Cold Regions Network was funded by the federal government under a climate change program. And it provided a springboard for us to bring together scientists from 8 universities and 4 federal agencies to focus on issues of changing water systems in Western Canada.
We're very fortunate in CCRN that we're building on a quarter century of major research programs that have addressed the global energy and water cycling experiment and other world climate research program studies. So the Mackenzie GWEC study of the 1990s and early 2000s, the DRY research network looking at droughts shortly after that, and the IP3 network looking at cold regions hydrology and hydrometeorology, all built up these models and has made development and established research basins and other things that are absolutely critical for us in moving forward with CCRN. And the great thing about CCRN is that we brought all that together and then expanded it and integrated it. And so it was really the wonderful timing for developing that network and building on this tremendous legacy that we had in Western Canada.
The Changing Cold Regions Network's integrated approach to climate and environmental change has been built on a legacy of focused research observatories and special sites. With environment and atmospheric data collected from across the region, the tundra and taiga of the Northwest Territories and Yukon in the north, the prairies and boreal forests of Alberta and Saskatchewan, and in the west, the headwaters in the Canadian Rockies of 2 of North America's largest river basins.
I'm in Wolf Creek studying the biogeochemistry of the system. CCRN gave me an opportunity to study a site that wouldn't have been funded otherwise. I noticed it's been a long-term hydrometric site, and there aren't a lot of those in the north. So it's one of a few in Canada and a few in the world.
We are looking at not only the hydrological cycle and the climate system, but we're looking at the terrestrial ecosystem, the forests, the shrubs, the soils, the carbon sequestration aspects of forests and soil microbes. One has to look at this system in an intact way because there are important interactions between vegetation and the water cycling. And then, of course, the water cycling helps determine the vegetation cover. I think we're fairly unique amongst water climate studies in that we have this strong ecosystem emphasis as well. And I might add that we also tie into the communities very, very strongly.
One of the things that we've learned from CCRN is that change is complex, and we can take even relatively small river basins, and they have different areas of elevation, different vegetation types, and they respond rather differently to change. So we can see different parts of these basins changing rapidly. We need to use our models to unscramble the complexity of the processes and then make better projections at the large scale. And that's enabling us to have more confidence in our predictions of the future.
The hydrological process studies that we've been conducting in the mountains have revealed several unknown phenomena that we've been able to incorporate in our hydrological predictive models. The models that we've developed, because they have a physical basis to them, will have applicability outside of the climate and environments that they were derived in. And so that physics base is very, very important because we'll be seeing weather patterns, climates, and physical environments in 50 years, 100 years that could be quite different from what we're seeing now.
We've been working on developing the cold regions hydrology model, which in its early days had a lot of development here in the Wolf Creek Research Basin. But all the input and the support I get from CCRN contributes to the adaptation that processes that we're carrying out. It's have had already a significant impact on daily life of Yukoners. Climate change is a reality here. We've seen very vivid changes, well, of course, in the temperature and precipitation regimes, but also streamflow regimes due to degrading permafrost, ablating glaciers.
What we've been able to do now is improve the physical basis of these models. So we've reduced the uncertainty of the predictions by improving these models, by improving the physics in them, by improving their description of the landscape, vegetation, and the streams, and also by improving the atmospheric inputs of these models by, for instance, driving them with future weather as opposed to future downscale climate. And future weather is what produces future hydrology. So that's a real landmark of CCRN.
The Weather and Research Forecast model, we call it WRF, is a regional climate model. It's capable to simulate the western part of Canada at 4-kilometer resolution. We use WRF to simulate 15 years in the past using historical data as a boundary condition, and then simulate in a very high resolution the atmospheric processes. To represent the future, we use a group of global climate models to create a representative environmental perturbation of a warmer climate, and it helps us to identify changes in the future considering the same internal variability that we have in the historical simulation. With that, we can compare both simulations.
CCRN researchers have developed the opportunity to better simulate hydrological processes, particularly in cold regions. Certainly researchers and practitioners at Environment and Climate Change Canada have strongly collaborated with CCRN to better simulate our water resources at the large scales. This includes the Mackenzie River Basin and the Saskatchewan River Basin. We have made major advancements with our models so that we're better able to simulate things like permafrost in the Mackenzie Basin. We have also made major advancements in capturing the complexity of prairie hydrology, particularly when we look at depressional storage and wetlands. We've also made major strides in incorporating the various water management structures in our models. This includes control dams for hydropower and dams for irrigation.
So we've got some of the world's best models of future climate, really high resolutions. We just need to translate that into better forecasts of river flows and floods. And then consider how the landscape will evolve, what's going to happen to the glaciers, what's happening to tree lines, to shrub tundra in the north, the thawing of permafrost, and changing patterns of precipitation. That's important for society, for example, hydropower and the competing needs, for water for use for agriculture, maintaining flows in our rivers for healthy ecosystems.
Prairies contain over 80% of Canada's agricultural land, and almost all of this area is limited by not enough moisture to allow crops to meet their production potential. With a changing climate, it is critical to understand how changes in precipitation and temperature will affect crops and livestock, what implications this has for pests that attack the crops, and the suitability of the land to grow a wider variety of crops. We have been working with the Changing Cold Regions Network to use high-resolution future climate data to advance our understanding of the vulnerability of prairie landscapes to climate extremes, such as droughts and floods, as these can have a devastating impact on agricultural production. This, in turn, will help agriculture remain competitive, sustainable, and capable of meeting an increasing food demand.
I think CCRN has allowed us to build much improved models of these processes. So we're in our fine-scale models, we're doing a much better job at representing the really complex environment of the prairies, where we have these networks of pothole prairie lakes. We're doing a better job at simulating the changing glacier environment and the groundwater systems. And that's enabling us to have more confidence in our predictions of the future. Western Canada has been experiencing some of the world's most rapid environmental and climatic change. By developing new cutting-edge science and modelling tools, the Changing Cold Regions Network is better prepared to predict the future of this changing environment. Taking what we've learned from the past, as well as from recent extremes of flood, drought and fire, we're able to make more advanced predictions. We hope that these will enable society to better manage the water needs of future agriculture, industry and communities while protecting our fragile ecosystems, and better managing risk from the more damaging extreme events that we predict will occur in the future.
We use high-resolution atmospheric models such as WRF to help us better understand the future climate. With 4-kilometer resolution, we're able to simulate the convection explicitly and the formation of the precipitation in a more realistic way. We are going to see a continuous warming across much of Western Canada through the 21st century. The seasonal average temperature increase could be up to 10 degrees C for the northern area. This warming is expected to be higher in northern Canada, with the largest temperature increases continuing to happen during the winter months. The summer months will see a lower rate of warming of 4 to 6 degrees C. Overall, our models suggest that we'll see a slightly increase in precipitation across the whole domain, with the highest increases happening during the fall and the winter months, and with higher increases in the north. Our models also suggest that we'll likely have an increase in precipitation extremes because of the higher temperatures and more water vapor held in the atmosphere. We'll experience more convective precipitation events, such as thunderstorms, which can bring more intensity rainfalls and hail. Other extreme precipitation events, like droughts, will also increase in frequency and not only just impact the agriculture sector, but may also lead to extreme fire years like we recently experienced across the Western Province and the territories from 2014 to 2017.
Climate is changing, and as it continues to change over the 21st century, the warming temperatures, longer growing seasons, and increases in plant water stress are expected to drive big shifts in vegetation across Western Canada, with prairie crop and grassland expanding northward into the southern boreal forest, deciduous trees replacing evergreens in parts of the central and northern boreal forest, and shrubs encroaching on tundra to the north. Some of the changes in vegetation, like the expansion of shrubs above the northern and alpine tree lines, will occur in response to climate change alone. Other vegetation changes will occur only after wildfire. In these cases, the impact of climate warming will be twofold. First, increasing the frequency and intensity of fire, which triggers change, and secondly, causing a loss of ecosystem resilience, so that after burning, a forest in the south may be replaced by shrubland or grassland, and an evergreen forest in the central boreal may come back as deciduous forest or mixed wood. In addition, there's a real possibility that northern evergreen forests growing on peaty soils will collapse as the permafrost melts, to be replaced by wetlands. These vegetation shifts, together with the melting of permafrost and the recession of glaciers, will have profound impacts on regional ecology and surface water resources, impacts that are perhaps as great as those of climate change itself.
We, interestingly, will still have a full winter in the alpine in this area, but at the lower elevations around it, the snow cover in the winter might be more ephemeral. It would be coming and going various times. We can expect rain any month of the year, temperatures above freezing any month of the year in the alpine, but still a spring snowmelt, though I'd expect it to be approximately a month and a half to 2 months earlier. We'll also experience extreme droughts in the forests and in the alpine regions, and probably more fires. So perhaps on the mountain slopes, reduced forest cover because of fire and expansion of grassland in the valley bottoms could well happen.
Growing crops on the prairies requires a balance, not just a balance in terms of having not too much moisture or too little moisture, but also having the moisture timed in a way that the crop can mature and the farmers can harvest the crop and get it off without damage. Well, an increase in temperature can lengthen the growing season and create more heat, particularly in some of the northern areas, and perhaps open some of those areas up for the types of crops that we're growing now, or in some of the areas where we currently are cultivating land, we can open up to a wider variety of crops. The concern, though, is that higher temperatures are going to create higher evapotranspiration, and this is going to mean that we will likely lose moisture faster over the course of the growing season. We expect that there's going to be lower snow cover on the prairies, lower snowpack in the mountains, and higher temperatures throughout the growing season and over winter. What this can mean is potentially lower flows for water, which could impact irrigation. It could mean lower soil moisture conditions in the spring, which could implicate the moisture availability for crops during the growing season. And the warmer temperatures could result in higher incidences of heat stress and create more favorable environments for pests.
So there's quite a few compensating factors when looking at these large river basins. They tend to integrate what we see with respect to the hydrological cycle. And so sometimes what you see is a small change perhaps in flow at the mouth of a very large river like the Mackenzie, but a lot of changes internally to the basin. However, we are seeing changes in the timing of flows, and that's pretty evident in most basins where we're seeing the peak flows occurring early in the summer, and we're also seeing in places like Saskatchewan longer duration of flow in the summer season, which we haven't seen before. That's certainly being predicted by the models for the future. It'll be interesting to see how we actually deal with that down the road, but for now, that's one of the big outcomes we're seeing. The other thing we're seeing is increased precipitation, particularly in the eastern prairies. We've had some significant events. These events we haven't seen historically, so we're noting with the models that the likelihood of those significant precipitation events in the late summer is likely going to increase. But of course, there's a lot of variability with flow on a year-to-year basis. So in a year where there's heavy snowpacks, there's still going to be high flows, and we're seeing actually a likely increase in extremes. So we think the drought periods are going to get longer, and we think the flood periods will be more frequent, and that seems to be appearing in the model.
Our early model outputs are suggesting that we will start to sort of cross a threshold of hydrological behavior in these cold mountain watersheds and northern watersheds. It will occur at the southern latitudes first and at the lower elevations first. We'll see a shift from a snowfall-dominated hydrological cycle to a rainfall runoff-dominated hydrological cycle. So in the last 4 years, we've seen the highest flows ever recorded and the driest droughts ever recorded. And it's that sequence of highs to lows, of extreme variability in the hydrology that may be the most difficult part to adapt to for Canadians in the Saskatchewan and Mackenzie River basins. We've improved our understanding of hydrological processes and the hydrological cycle in this cold region. We're taking that information and improving our models.
The rapid and extensive changes to water that we're seeing in Canada are mirrored throughout the world's cold regions, the Himalayas, Andes, Alps, Tibetan Plateau, and these supply water to half of the global population. These changes pose existential threats for society. We live in an ever-connected world where flood and droughts affect not only local populations, but national economies and global trade. This unprecedented change poses critical challenges to manage water security in a future that will always be uncertain, and for science to provide the information and tools needed to adapt to this change. We hope that CCRN's new data, science and models will make a difference, but this work must continue so that we can observe and better understand the implications of these remarkable changes and provide useful information for managers, policymakers and the public. And we will all have to do our part in managing and adapting to change and shaping our future in a warmer world.